Hello science junkies, today we're going to talk about a really fascinating topic, sonic booms. Surely, just like me, most of you want to know why these sonic booms happen, because as the plane goes faster than sound, it leaves it behind. When it arrives and passes you, that's when you hear them all at once. However, that's not exactly how it works. Because look at this video, when the first stages of the Falcon Heavy landed, the famous rocket that took the car into orbit, etc. Look at the craziness that was heard. Yes, you can hear really weird explosions. Well, first of all, let me clarify that in the video, when some little red balls appear in the animations. Each ball represents an air molecule. Our surroundings are air, which consists of tiny molecules. Let's proceed. Sound is a longitudinal pressure wave. Let's break down these three words to understand their meaning, because this is key. Alright, first, wave. The definition of a wave is the propagation of a disturbance through space. Okay, but what does that mean? Well, for example, ocean waves. The water molecules actually only move up and down. They do it in sync, making it seem like they're moving forward, but they're actually just moving up and down. Alright, now let's understand what longitudinal means. It's super simple. I'll give you two examples. Ocean waves are not longitudinal waves. Why? It's simple. Water particles move up and down as the wave moves forward or backward. So they move like this, and it seems like the wave goes that way. Alright, those are transverse waves, but longitudinal waves move in the same direction as the wave. So if the wave goes, for example, towards the camera, the particles are going to move forward. They then return to their position. That's a longitudinal wave. During the video, remember that sound is a longitudinal pressure wave. Okay, let's look at some examples to try to understand this a little better. When you touch your throat while speaking, you feel vibrations from your vocal cords. What's causing this? Okay, well, the only thing that's happening is that the vocal cords are vibrating in such a way that they're altering the air. In other words, they're moving air molecules in a way that moves a single air molecule. That one pushes the one next to it, and so on. And that's the pressure wave I was talking about. Why? Well, because when they're pushing against each other, the pressure is much higher than when one has already pushed the other and they're separated. So how do we detect sound? Well, the ear has the ability to perceive these pressure waves in such a way that our ear is able to detect the pressure in the air that reaches it. And that information is transmitted to the brain as if it were a sound. Okay, and one thing I haven't mentioned, which is super important, is that sound propagates in all directions. That is, it does so in a spherical way. Should we include a person clapping? As mentioned earlier, the waves propagate in all directions. The wave we see is nothing more than those pressure waves I mentioned earlier. So where we're seeing the line, what we really have in real life are air molecules that are closer together than in the other part of the drawing. Well, then we can see that sound travels at a certain speed, and this speed is predefined. At sea level, it's around 1,000 kilometers per hour. But the most important thing of all is that it's known as the speed of sound, but it's not just the speed of sound. It's the speed at which pressure waves propagate through space. So if I, for example, do this with my hand, there I've been pushing the air molecules, but that doesn't produce any sound. Why? I haven't made it vibrate like my vocal cords do, but pressure waves propagate at the speed of sound. You might ask, why is it called the speed of sound and not the speed of propagation of pressure waves? This is a very important question. It sounds better to say speed of sound, doesn't it? Alright, come on, let's get to it. Now let's say we have our person who's clapping, but now they're moving. We can see that in the front, the waves are much closer together than in the back, and this is because of the movement. This phenomenon is called the Doppler effect, as exemplified by the sound of a passing ambulance. Until it passes you, it sounds one way, and once it has passed you, it sounds different. That's because the sound waves coming toward you until it passes by are very close together. However, once it passes you, they start to spread apart. Alright, let's take it up a notch, and now suppose that our person is moving exactly at the speed of sound. In the front, the waves converge at a single point, while in the back, they spread out and are widely spaced. Now, let's assume they're traveling faster than the speed of sound. As expected, the waves are left behind, forming a cone. When the cone reaches us, all the sounds arrive at once, and this acts like an amplifier. Well, here we have to introduce the Mach number. The Mach number is nothing complicated, it's super easy. It's basically the speed you're going divided by the speed of sound. If you're traveling faster than the speed of sound, the Mach number will exceed 1. Mach 1 means traveling at the speed of sound. Mach 0 point something indicates a speed slower than the speed of sound. Many people may have followed me up to this point, as it's somewhat intuitive. However, now we'll delve deeper into the really interesting aspects of the subject. Because if you think about it, when the rockets landed, there wasn't any. Why so many explosions? Why? Well, that's what we're going to look at. Okay, as I said before, the speed of sound is also the speed at which pressure waves travel through the air. So when a plane is traveling below the speed of sound, what happens is that the air molecules it's going to collide with already know the plane is coming. I mean, you know what I mean. The air particles the plane has collided with produce pressure waves that move faster than the plane. Therefore, they inform, quote-unquote, the molecules that are farther away to be careful. The plane is coming, move aside a bit so those air molecules move out of the way for the plane to pass. It's like trying to catch pollen in the air, but being unable to. With pollen, you keep trying to grab it like this, but you can't because it's like it's running away from you. When you move your hand, you create pressure waves that move faster than your hand. Thus, they reach the pollen first and push it away, as if warning, watch out, a hand is coming. This is clearly visible in the video. Let's see, this is a test in a wind tunnel. Basically what they did was put some smoke or something like that so you can see how the air reacts. This one was moving slower than sound speed. They ensured the air remained stationary by blowing it from the same location continuously. The wing profile is moving as they extend the flap, the back part that's visibly moving. Observe how all the air is moving as a result. And you might ask me why. The air anticipates what it will encounter based on the pressure waves. So it adapts itself to fit the shape of the wing, but here's the key to everything. When a plane flies at supersonic speed, it can't do this because it's traveling faster than the pressure waves, as previously explained. As the plane arrives, the particle must instantly move, producing incredible pressure waves. So that sudden movement they make to get out of the way. Sound is transmitted as a wave because air molecules move sideways, pushing adjacent molecules. Therefore, it pushes it, and that one pushes the next one beside it, and that's how it spreads, and this pressure wave is created. With the pollen example, if we moved our hand at a higher speed, the speed of sound, which is a bit confusing, but I hope you understand. If we moved it faster than that speed, the pollen wouldn't be able to escape, and we would definitely catch it. You may wonder how this relates to what I said earlier. It's easy to connect the dots. Basically, what happens is that it's such a sudden pressure wave that it acts like an incredible sound. In other words, the sound produced when a plane passes at supersonic speed. The boom you hear is a mix of engine noise and the sound of air being rapidly displaced by the approaching plane. You might think that sounds crazy. What are you saying? Well, yes, because when a meteorite comes and the meteorite doesn't have engines, doesn't have anything, a sonic boom is produced. Since meteorites are typically several meters long, the air they collide with must be displaced several meters instantly. The meteorite's supersonic speed creates an incredible pressure wave. This is precisely what occurs when the Falcon 9 lands. SpaceX engineers state that each Falcon 9 produces 3 sonic booms. The first one occurs at the rocket's bottom as it descends at supersonic speed, forcing the air to move out of the way instantly. They say the second one is produced by the Falcon 9's legs. Right? Well, exactly for the same reason, because it has the legs like that, and all the air that's underneath the legs, well, that hits the legs, has to move out of the way instantly. Another pressure wave is produced there. Incredible. The other one was at the top, which also has some other weird legs. That's why each Falcon 9 has 3. It's crucial to note that this immense pressure wave can shatter glass and rupture eardrums. Did you know that you can only exceed the speed of sound, Mach 1, when flying over the sea? It's wild! That's because if not, even if the plane is super high, it will shatter all the glass below. Sometimes when planes fly at supersonic speed, you can see that it creates something like a cloud, a kind of strange condensation. And this is because the plane collides with the air, and in the cone that forms there, the pressure is very high. So that condensation happens because of the big difference caused by the high pressure in the cone. And when the cone passes, there's suddenly a very sharp drop in pressure, and that's when condensation occurs. Some examples of shock waves can happen when there's a bomb or something you might not know about. It's that with a whip. A whip sounds so strange because it breaks the sound barrier. Yankees, I hope you grasped it since it's a genuinely amazing subject. And science rules.